your breakfast this morning still exists. Not the memory of it, the actual event, physically, mathematically, structurally real, preserved in the equations that govern every particle in the universe. Every law of physics we have ever written is perfectly happy running backward through time. Newton, Maxwell, Einstein, Schrödinger, none of their equations contains a single line that erases the past. And yet here you are, completely unable to reach it. That contradiction has been sitting unresolved in physics for 150 years. But tonight we chase it all the way down, and the answer gets stranger the deeper we go. If you are new, welcome to Sundown Science. Subscribe and get comfortable. We are about to follow time's arrow from the microscopic world, where physics has no preferred direction, through thermodynamics, quantum mechanics, and the geometry of space-time, and find that every framework we have preserves the past perfectly while making it permanently unreachable. We will also explore why that unreachability is not a law of nature, but a consequence of how the universe happened to begin, and why that one word, happened, is the most honest and most disturbing word in all of cosmology. Now settle in and let's ease into this. Part 1. The moment that shouldn't exist. There is something happening right now that physics cannot explain. Not in a vague, hand-wavy, science doesn't know everything kind of way. In a very specific, very precise, very embarrassing kind of way. Because right now, as you sit wherever you are sitting, watching this video, the equations that describe every particle, every force, every interaction in the known universe are quietly insisting that this moment, this exact moment, and every moment before it are all equally, permanently, indestructibly real, not as memory, not as a fading impression in someone's brain, as a structural feature of the mathematics of reality itself. And yet, here you are, completely unable to reach any of them. Let's slow that down, because the strangeness of it gets lost if you move too fast. Think about your morning. Whatever happened, coffee, a shower, the sound of traffic, someone you spoke to, a thought you had while half awake, all of that is gone now. That's how it feels. That's how it always feels. Time moves, things pass. The present becomes the past, and the past becomes inaccessible. This is so fundamental to human experience that we've built entire religions around it, entire philosophies of loss and impermanence, entire artistic traditions devoted to the ache of things that cannot be returned to. The pastness of the past feels like the most obvious fact in the world, except it isn't a fact that physics supports. Here is what physics actually says. Newton's equations, the ones that describe how objects move, how forces act, how momentum transfers, are perfectly, completely, mathematically symmetric in time. You can run them forward and you get the correct trajectory of a billiard ball, a planet, a cannonball. You can run them backward and you get an equally valid, equally correct, equally physical trajectory. The equations don't know which direction is forward. They don't have a preference. The variable for time in Newton's laws sits inside an equation that treats positive time and negative time with complete indifference. Maxwell's equations, the four equations that govern electricity, magnetism, and light, the equations that are so fundamental that Einstein used their inconsistency with Newtonian mechanics as the launching point for special relativity, are also time symmetric. Every electromagnetic wave that travels forward in time has a mathematically identical twin that travels backward in time. The equations permit both. We call one kind the retarded solution and the other the advanced solution, which are just technical names for forward-going and backward-going electromagnetic waves. The retarded solutions are the ones we observe, but the advanced solutions, the ones running backward through time, are not forbidden by Maxwell's equations. They simply require a different set of boundary conditions, a different configuration of the universe around them. The math doesn't care. And then there is the Schrödinger equation, which governs quantum mechanics, the behavior of particles at the smallest scales we can probe. The Schrödinger equation is also time-symmetric. The wave function that describes a quantum system evolves forward in time in a way that is called unitary, which is a technical term that contains within it a very profound implication. Unitary evolution means that the evolution is reversible. It means that no information is ever lost. It means that the full history of a quantum system is encoded, permanently and completely, in its current state. Given the current state of a closed quantum system and the equations that govern it, you could in principle run the evolution backward and reconstruct every prior state exactly, not approximately, exactly. So we have Newton saying the past is accessible in principle. We have Maxwell saying the past is accessible in principle. We have Schrödinger saying the past is not only accessible, but actually encoded in the present state of reality. And yet your coffee cools and never spontaneously heats back up. And yet the egg that fell from your counter this morning shattered into pieces and has not once, in the history of human observation, reassembled itself and jumped back up to the countertop. And yet you are moving through time in one direction, irreversibly, with the sensation that everything behind you is sealed off and gone. This is not a minor philosophical puzzle. This is a direct contradiction between the most fundamental laws of physics and the most basic feature of experienced reality. And the contradiction has been sitting there, unresolved, for approximately 150 years. The laws of physics contain no erase operator. There is no equation, no fundamental interaction, no force in the standard model of particle physics that takes a state of the universe and deletes it. What happened is not unmade by any law we know. It is retained, encoded, preserved in the microscopic structure of reality, in the positions of atoms, in the states of quantum fields, in the entanglement structure of particles that once interacted. The past is not gone, it is hidden. It is scrambled beyond any practical reconstruction, but it is there, and that distinction between erased and hidden, between gone and unreachable, is not a semantic game. It is the actual foundational mystery that sits under everything we think we understand about time, causality, memory, and the direction in which the universe is running. If nothing deletes the past, then what exactly are you missing when you try to go back? That is the question, and chasing it down takes you to some of the strangest places physics has ever gone. Part 2. The film that runs both ways. Imagine you are watching a film of a gas of molecules moving around inside a box. Billions and billions of tiny particles bouncing off each other, colliding, transferring momentum, ricocheting at angles determined by their relative velocities at the moment of contact. The film looks perfectly ordinary. The physics looks correct. Now imagine I reversed the film, played it backward, so every particle that was moving left is now moving right. Every particle gaining speed is now losing speed. Every trajectory is exactly mirrored in time. Here is the thing that should stop you cold. You could not tell the difference. There is no physical test you could perform, no equation you could write down, no law you could invoke that would allow you to identify which version of the film was forward and which was backward. At the level of individual particle collisions, the physics is exactly the same in both directions. This is not a metaphor. It is a mathematical theorem that follows directly from the structure of classical and quantum mechanics. Take any collision between two gas molecules. One molecule approaches another, they interact, they exchange momentum, they fly apart in new directions. Now reverse every velocity. Run the interaction backward. The reverse collision is just as valid, just as physically permitted, just as consistent with Newton's laws as the forward one. The equations governing the collision do not point a finger at time and say, this way. They are agnostic. They are to use the technical term, time reversal invariant. The same is true for electromagnetic radiation. When an accelerating charge emits a radio wave, that wave propagates outward in time. But Maxwell's equations also allow the time-reversed version, a wave converging inward from all directions, arriving at a charge and being absorbed. Both solutions exist in the mathematics. We only see outgoing waves in practice, waves that spread forward in time from their sources. But that asymmetry does not come from Maxwell's equations. It comes from something else entirely. It comes from the arrangement of the universe around the emitting charge, from the fact that the surrounding universe has the right structure to absorb outgoing waves, but not to produce precisely coordinated incoming waves. The equation permits both. The universe, or rather, the specific universe we happen to inhabit, selects one. This is where physics starts pulling the rug out from under intuition. Because the usual story about time, the story where the past is gone and the future hasn't happened yet and the present is special and real, is not written into the fundamental laws of nature. It is written into the boundary conditions of the universe. The distinction is everything. A law is something that must be obeyed always and everywhere, that follows from the deep structure of reality. A boundary condition is a description of the specific state that some particular system happens to be in. Laws govern how things evolve. Boundary conditions describe where things started. And what physicists discovered, slowly and with great reluctance, is that the arrow of time, the felt, experienced, undeniable sense that time moves in one direction, is not a law. It is a consequence of where the universe started. There is an intuition that resists this conclusion, and it is worth confronting directly, because it is the same intuition that makes the broken egg feel like a permanent truth rather than a statistical tendency. If I showed you a film of an egg falling from a counter and shattering on the floor, you would immediately, correctly, intuitively identify it as running forward in time. If I showed you a film of egg fragments assembling themselves from the floor, flying upward, and landing intact on the counter, you would immediately, correctly, intuitively know that the film was running backward. But here is the devastating question that Boltzmann was asking in the 1870s. Why? What law, exactly, is being violated in the second film? Can you write it down? Can you point to the specific equation that prohibits egg fragments from spontaneously coordinating their velocities, their positions, their mutual interactions, in precisely the right way to converge back into a whole egg? You cannot, because no such law exists. What exists instead is probability. The egg fragments reassembling is not forbidden. It is just so extraordinarily, almost inconceivably improbable that it has never been observed in the history of human civilization, and almost certainly never will be. But almost certainly never will be observed, and physically impossible are not the same thing. They feel identical from the inside. They lead to the same practical predictions, but they are conceptually completely different, and the difference turns out to be one of the deepest facts about the universe. This is the first crack in the ordinary story of time. The direction of time is not enforced by law, it is enforced by probability. And probability, unlike law, has an asterisk. It has an explanation. It has a reason. And that reason, where it comes from, why it points the way it does, what set it in motion, is one of the most genuinely open questions in all of physics. If probability is what makes the past feel sealed and the future feel open, then the question of why time has a direction becomes the question of why the universe is structured so that the probabilities all point the same way, which is a very different question, and a much harder one, and one that leads somewhere very strange, which is where we are going next. Part 3. The first crack in reality. In 1865, Rudolf Clausius stated something that sounded almost obvious, but contained within it the seeds of one of the deepest crises in the history of science. He said that in any isolated physical process, A quantity he called entropy either increases or stays the same. It never decreases. He called this the second law of thermodynamics. Heat flows from hot to cold. Gas expands to fill its container. Ordered structures dissolve into disorder. And the quantity that measures this tendency, entropy, always goes up, never down, across all processes in all isolated systems everywhere in the universe. That was the second law. It sounded like a law. It had the grammatical structure of a law. It was presented as a law. It was even numbered among the laws of thermodynamics, right there between the first law and the third. But a decade later, Ludwig Boltzmann did something extraordinary. He derived the second law from first principles. He showed, using the reversible microscopic laws of classical mechanics, exactly why entropy increases. And in doing so, he accidentally revealed something that Clausius had hidden inside the word law. Because what Boltzmann showed was that entropy increase is not fundamental, it is statistical. And statistical, as we have just established, is not the same as inevitable. To understand what Boltzmann did, you need to understand what he meant by entropy. Clausius had defined entropy as a thermodynamic quantity, something you could measure in a laboratory, related to heat flow and temperature. Boltzmann redefined it at a microscopic level, and in doing so, transformed what it meant. His equation, which is carved on his tombstone in Vienna, in one of the most elegant scientific tributes ever paid to a human being, is S equals K times the logarithm of W. In that equation, S is entropy, K is Boltzmann's constant, a tiny number that bridges the microscopic and macroscopic worlds, and W is the number of microscopic configurations, or microstates, that correspond to the macroscopic state of the system you are describing. This is worth unwrapping slowly, because it is genuinely the key to everything. When you say that a cup of coffee is hot, or that a gas is in a certain pressure and temperature, you are describing a macroscopic state. You are saying something about average properties, average kinetic energy of molecules, average momentum transfers at the walls, average density. But that macroscopic description is consistent with an enormous number of different possible microscopic arrangements. The specific positions and velocities of every individual molecule could be any one of a fantastically large number of different configurations, and the cup would still look and feel exactly the same to you from the outside. These are the microstates. And Boltzmann's insight was that entropy is just a count of them. A state with high entropy has many microstates that look like it. A state with low entropy has few. And now the logic of why entropy increases becomes almost obvious once you see it. If you have a system in a low entropy state, say all the gas molecules crammed into one corner of a box, then there are very few microscopic configurations that correspond to that arrangement. If the molecules evolve randomly, according to the microscopic laws, they are vastly, overwhelmingly more likely to end up in one of the many more configurations that correspond to the gas being spread evenly throughout the box. Not because a law pushes them there, because there are simply so many more places for them to be. They spread out for the same reason that if you shuffle a deck of cards, you almost certainly will not get them back in perfect order. Not because something prevents it, because the ordered arrangement is just one configuration out of a colossal number of possibilities, and random shuffling is unlikely to land on it. This is what time's arrow reduces to in Boltzmann's framework. The universe evolves from lower entropy states to higher entropy states, not because any law compels it, but because higher entropy states are more numerous. There are more ways to be disordered than ordered. The microscopic evolution is reversible. The macroscopic tendency is overwhelmingly one-directional, and the direction it tends toward is what we call the future. Arthur Eddington, in 1927, gave this one-directional tendency a name that has stuck ever since. He called it the arrow of time, and he meant something quite specific by it. He meant that if you want to know which direction in time is the future and which is the past, you look at entropy. The future is the direction in which entropy increases. The past is the direction from which the universe came, the direction of lower entropy. Entropy is the only physical quantity that reliably distinguishes before from after. Everything else, every fundamental equation in physics, would look equally valid run in either direction. Entropy is the one asymmetry, the one pointer, the one clock built into the structure of macroscopic reality. Except, and this is the crack that Boltzmann himself recognized, and that kept him awake at night until his death, this explanation only works if the universe started in a state of very low entropy. If the universe had always been in equilibrium, there would be no arrow. Entropy would already be at its maximum. Everything would be uniform and featureless, and there would be no direction in which entropy could increase, because it would already be as high as it could go. The arrow of time, in Boltzmann's framework, does not emerge from the laws of physics. It emerges from the initial conditions of the universe, which means it has an explanation only if the universe's beginning has an explanation. And that, as it turns out, is where things get genuinely strange, because the beginning that physics requires in order to explain the arrow of time is a beginning of almost impossible precision, a beginning so specific, so tuned, so improbably exact, that when Roger Penrose calculated the odds, he arrived at a number that makes the total number of atoms in the observable universe look like a rounding error. Part 4. Boltzmann's dangerous idea. There is a moment in the history of physics that deserves to be called a crisis, but has largely been absorbed into the curriculum and taught as if it were routine. The moment is this. Boltzmann succeeded. He derived the second law. He showed where entropy comes from and why it increases. He built a rigorous, mathematically sophisticated framework, statistical mechanics, that connected the microscopic world of atoms to the macroscopic world of temperature and pressure and heat flow. He did something that had never been done before, which was to reduce a macroscopic law of nature to the statistical behavior of microscopic constituents. And then, in working through the implications of what he had done, he found something that threatened to undercut the very law he had just derived. The problem is called the reversibility objection, and it was first stated clearly by Boltzmann's friend and colleague Joseph Loschmidt. The argument goes like this. Statistical mechanics is built on classical mechanics. Classical mechanics is time reversible. Therefore, statistical mechanics is time reversible, which means that for every trajectory through phase space that increases entropy, there exists a time-reversed trajectory that decreases entropy and is equally permitted by the microscopic laws. So why does entropy always increase? Boltzmann said it is because higher entropy states have more microstates, but the time-reversed argument applies equally in both directions. Why doesn't entropy increase in both directions, toward the past as well as toward the future? Boltzmann's answer to this was subtle and deep, and it is the same answer that modern physics gives, though the language has changed. The reason entropy does not increase in both directions is that we do not observe systems starting from maximum entropy and evolving toward lower entropy. We observe systems starting from relatively low entropy. The initial condition is everything. The second law is not a law in the sense that it follows from the dynamical equations. It is a probabilistic tendency that follows from a combination of the dynamical equations and the initial condition of the system. Change the initial condition, start with a system already at maximum entropy, and you get no second law, no arrow of time, no thermodynamic direction. The second law is a statement about where we are in the universe's history, not a fundamental constraint on physics. This realization generates a problem immediately. because if the second law is a consequence of the initial condition, then explaining the arrow of time requires explaining the initial condition. And explaining the initial condition of the universe, why it started in a state of low entropy rather than high entropy, is not something that statistical mechanics can do from the inside. Statistical mechanics describes how systems evolve. It does not explain why they started where they did. That question reaches beyond the boundary of the theory. Here is the picture that falls out of Boltzmann's statistical mechanics when you take it seriously. Every macroscopic state of any system corresponds to a region of phase space, the abstract mathematical space that contains all possible microscopic configurations. The size of that region, loosely speaking, is what Boltzmann's W counts, and the logarithm of W is entropy. The universe, as a whole, occupies some point in its phase space at any given moment. The microscopic laws describe how that point moves through phase space over time. The overwhelming majority of phase space corresponds to high entropy configurations, the universe at or near thermal equilibrium, uniform, featureless, with no gradients of temperature or pressure, no stars, no planets, no life. The region of phase space corresponding to the low entropy early universe is fantastically tiny compared to the total, and this means that the universe starting in the state it started in is not what you would predict from statistical reasoning. It is the opposite of what you would predict. Statistical reasoning says systems should be near maximum entropy. The early universe was nowhere near maximum entropy. Something else must explain that. And here is where the past's permanence connects back to the arrow of time in a way that should make you uncomfortable. The reason you cannot go back is not that the past has been erased. The reason is that getting back to the past requires your current state to evolve back through time toward a lower entropy configuration. And the laws say that trajectory is so improbable as to be effectively unreachable. The past is preserved in the microscopic structure of the universe, but reaching it requires entropy to decrease, which requires traversing a region of phase space so tiny that no realistic physical process could navigate there. The past is not gone. It is locked behind a probability barrier so extreme that it functions for all practical purposes as a physical wall, but practical impossibility and fundamental impossibility are different things, and keeping that difference clear is essential to understanding what follows. Part 5. The universe had to begin wrong. Roger Penrose is one of the most careful mathematical physicists alive, and when he calculated how special the initial state of the universe had to be in order to produce the arrow of time we observe, he arrived at a number that most people who hear it simply cannot process. The number is 10 raised to the power of 10 raised to the power of 123. Write that out, and it is a 1 followed by more zeros than you could fit in the observable universe if you wrote 10 on every proton. It is not a number that corresponds to anything human beings encounter in any other context. It is the estimated probability, in Penrose's calculation, of randomly selecting from all possible initial states of the universe, one that has low enough entropy to produce the arrow of time we observe. The probability is not low. It is not very low. It is not incredibly low. It is so incomprehensibly, catastrophically small that even describing it as almost impossible is a severe understatement. What this number is measuring is the following. The Big Bang produced a universe in a state of extremely low entropy. Not low compared to where it was a year later or a billion years later. Low in absolute terms. Low in terms of the total entropy the universe could possibly have given all the matter and energy it contains. The universe did not start out at or near thermal equilibrium and then develop structure. It started in a state of extraordinary, almost implausible order and has been evolving toward disorder ever since. The hot, dense, early universe was not disordered in the thermodynamic sense. It was uniform, which is to say it had low, gravitational entropy. Gravity pulls matter together. Maximum gravitational entropy is a universe full of black holes. Minimum gravitational entropy is a universe with matter spread uniformly. The early universe was close to the gravitational minimum, and it has been climbing toward the gravitational maximum ever since, forming stars and galaxies and eventually black holes along the way. David Albert, the philosopher of physics at Columbia University, gave this initial condition a name, the past hypothesis. He proposed, not as a derivation but as an explicit additional assumption, that the laws of physics have to be supplemented by a boundary condition that specifies the early universe's low entropy state. Without the past hypothesis, statistical mechanics gives you no arrow of time. With it, everything follows. The coffee cools, the eggs break, time runs in one direction. But the past hypothesis is not derived, it is assumed, it is inserted into the theory by hand, because without it, the theory gives the wrong answer. That is, to put it plainly, an incomplete theory. A derivation that depends on an underived assumption is not a full explanation. It is an explanation that has been pushed one level deeper without being resolved. The cosmic microwave background, the faint glow of radiation left over from the early universe, uniform to about 1 part in 100,000 across the entire sky, is the best evidence we have for the low entropy initial state. That uniformity is not what you would expect from a random initial condition. A random universe would be far more irregular, far more lumpy, far more varied. The smoothness of the early universe is precisely what Penrose's improbable number is measuring. The universe began in a state so ordered that random chance cannot account for it. Inflation, the theory proposed by Alan Guth in 1980 and developed by André Linde and others, is the leading attempt to explain this smoothness. The idea is that in the first tiny fraction of the first second after the Big Bang, the universe underwent a period of exponential expansion, during which quantum fluctuations were stretched to cosmic scales and any initial irregularities were smoothed out. Inflation explains a great deal. It explains why the universe is spatially flat. It explains the specific pattern of fluctuations in the cosmic microwave background. It makes predictions that have been confirmed by observation. It is the most successful cosmological theory we have for explaining the early universe's structure. But inflation does not solve the entropy problem. It relocates it. If you ask what set the conditions for inflation itself, what made the inflaton field start in a configuration that would drive exponential expansion, you find that the pre-inflationary state must also have been extremely special. Inflation does not generate low entropy from high entropy. It takes a particular initial condition and evolves it into the universe we see. But the initial condition inflation requires is itself improbable. The puzzle is not answered. It is moved one step earlier in the timeline, to a moment even further from direct observation, where our theories become even more speculative. This is the situation physics is in. The arrow of time, the feature of reality that makes the past inaccessible, that prevents you from returning to yesterday, that makes entropy increase rather than decrease, depends entirely on the universe having started in an extraordinarily, implausibly, perhaps inexplicably low entropy state. Nobody knows why it did, nobody has derived it. Every attempt to explain it either assumes it or relocates it. And that means the question of why you cannot go back to the past, why the past is sealed off from you, is at its root tied to one of the deepest unanswered questions in all of cosmology. Why did the universe begin the way it did? Part 6. The Boltzmann Brain Collapse. Before moving on, there is a reductio ad absurdum that Boltzmann's own framework generates, and it deserves a brief mention because it illustrates just how seriously the entropy problem has resisted resolution. If entropy increase is purely statistical, if the second law is just a statement about probability, then consider the following. The most likely explanation for any low entropy observation is not that the universe has been evolving for 14 billion years from an even lower entropy beginning. The most likely explanation is that the low entropy observation, including your brain, your memories, everything you think you know about your past, spontaneously fluctuated into existence from a higher entropy background just now, a momentarily structured configuration arising from thermal fluctuations, conscious for a brief instant before dissolving back into equilibrium. This is what has come to be called a Boltzmann brain, and while it sounds absurd, the statistical argument for it is, within a pure equilibrium framework, actually stronger than the argument for a real cosmological history. The spontaneous fluctuation of a single brain is vastly more probable than the spontaneous fluctuation of an entire low-entropy universe. Modern cosmology rejects the Boltzmann brain scenario, not because it has been disproved, but because it is self-defeating. Any theoretical framework that predicts your memories are probably false is a theoretical framework you cannot trust. The existence of Boltzmann brains as a theoretical prediction is taken as evidence that the statistical equilibrium fluctuation approach to explaining the arrow of time is fundamentally incomplete. Something more than pure statistics is needed. But what that something is, whether it is a new physical principle, a new understanding of quantum gravity, a selection effect, or something else entirely, remains genuinely open. What Boltzmann brains show, in the context of our central question, is this: the past that you remember, the past that you cannot return to, is not merely a statistical tendency. The stability of the past as something real and reconstructible from evidence, the fact that your memories are probably not random fluctuations, requires a cosmological initial condition, not just a law of averages. The past's reality is bound up with the universe's origin in a way that pure probability cannot explain, and that connection will run through everything that follows. Part 7. The Block Universe. In 1905, Albert Einstein published the special theory of relativity, and among its many consequences was one that, if you follow it to its logical conclusion, fundamentally changes what it means for the past to exist. The starting point is the relativity of simultaneity. Einstein showed that two observers moving relative to each other will disagree about whether two spatially separated events happen at the same time, not because of measurement error, not because of signal delays, but fundamentally as a matter of the structure of space-time. What is now for one observer is not now for another observer moving at a different velocity. The present moment is not a universal feature of reality. It is observer-dependent. This has an implication that takes some working through, but leads somewhere extraordinary. If there is no universal now, if different observers slice up space-time into past, present, and future in different ways, then the distinction between past, present, and future cannot be a fundamental feature of reality. The distinction must be, in some sense, a feature of how a particular observer relates to the universe, not a feature of the universe itself. And if the present has no universal definition, then neither does the past. What is in my absolute past may not be in your absolute past. The universe does not have a single, objectively agreed upon what has already happened. What replaces the naive picture of a flowing present is a four-dimensional structure, space-time. The universe, in relativity, is not a three-dimensional space that evolves through time. It is a four-dimensional block in which time is one of the dimensions. Every event, every point in space-time has coordinates in all four dimensions. Your birth, your first memory, the asteroid impact that killed the dinosaurs 66 million years ago, the moment you are reading this, the heat death of the universe tens of trillions of years from now, all of these events are coordinates in the four-dimensional block. None of them is more or less real than any other. None of them has a special status as the present. The present is just the slice through the block that a particular observer happens to be located at, given their position and velocity. This view of space-time is called the block universe, or the eternalist view of time, and it is the picture that falls most naturally out of special and general relativity. In the block universe, the past is not gone. It is not erased. It is simply elsewhere in the four-dimensional structure. Your breakfast this morning is as real and as present as you are. It is just located at different space-time coordinates. The Big Bang is real. The far future is real in the same sense. All of time exists, all at once, as a static structure. The word exists becomes tricky here, because exists normally implies exists now, and now has become observer dependent. But the technical claim is precise. All events in space-time have equal ontological status. They are all real in the same sense. None of them is privileged as more actual than the others. The implication for the question of why you cannot return to the past is immediate and strange. In the block universe, you are not separated from the past by an arrow of time. You are separated from the past by displacement in a spatial direction, the time direction of the space-time manifold. Going back to the past would be like traveling in a spatial direction, not forward but backward, not down but up. The past is not gone. It is there. It is simply in a direction you cannot travel. Now, you might say, why can you travel in spatial directions but not in the time direction? That is exactly the right question. And the answer is not that the time direction is metaphysically different from the spatial directions. In the geometry of space-time, the time direction and the spatial directions are all dimensions of the same manifold, related by Lorentz transformations, linked by the speed of light. The difference between them is not categorical. It is geometric. The space-time interval, the quantity that relativity uses to measure distances in four-dimensional space-time, has a different sign for the time component than for the space components. This is not a profound philosophical difference. It is a sign difference in a metric. But that sign difference, combined with the constraint that all massive objects must travel along time-like paths and cannot travel faster than light, means that your future lies within a cone-shaped region of space-time, the forward light cone, and you are constrained to move within it. Moving backward in time would require exiting that cone, which the laws of physics do not allow for any massive object. So the block universe tells you that the past exists, fully and completely, as real as you are. But it also tells you that the structure of space-time geometry, combined with the constraint of causality, seals it off from you. You are embedded in a geometric structure from which past regions are structurally unreachable, not absent. This is precisely the distinction the central puzzle demands. Not erased, unreachable, not gone, inaccessible. Every moment of your life is still there, fixed in the geometry of space-time, real as a coordinate. You simply cannot travel to it. Which raises the question, what exactly is doing the preventing? The geometry? The physics? Something deeper? That is where quantum mechanics enters the story. Part 8. Quantum Memory of Reality. The Schrödinger equation governs the evolution of quantum systems, and it is one of the most precisely tested equations in all of science. Its predictions have been verified to accuracy levels that exceed 10 parts per billion. It has been tested across every domain of quantum physics, from single electrons to superconducting circuits involving billions of electrons behaving coherently. It describes the behavior of atoms, molecules, photons, nuclei, and quantum fields with remarkable precision. And, built into its structure, not as an approximation, not as a model, but as a mathematical necessity, is a property called unitarity. Unitary evolution means that the mathematical transformation that the Schrödinger equation applies to a quantum state over time is a unitary transformation, one that preserves the inner product of the state with itself, which is equivalent to saying it preserves all information about the state. A unitary transformation is reversible. Given the final state of a quantum system that has evolved unitarily, you can, in principle, apply the inverse transformation, and recover the exact initial state. No information is gained. No information is lost. The quantum state of a closed system evolves, but the full information content of its history is always present, always accessible in principle in the current state of the system. This is not a loose statement. It is a theorem. If quantum mechanics is correct, and if the universe is a closed quantum system, which it must be, by definition, then the quantum state of the universe contains, embedded within it, the complete quantum history of the universe, not approximately, not in some encoded form that requires additional information to decode. Exactly. The current state of the universe's quantum wave function is related to every prior state by a unitary transformation that can, in principle, be inverted. Let us sit with that for a moment. The moment your coffee was hot, the moment the egg was whole, the moment you were born, these are not deleted from the quantum state of the universe. They are encoded in it. The transformation from those states to the current state is unitary, which means it is invertible, which means those states can be recovered in principle by running the transformation backward. The past is not only preserved geometrically in the block universe sense, it is preserved informationally in the quantum mechanical sense. Two independent frameworks, coming from completely different directions, relativistic geometry and quantum information theory, both converge on the same conclusion. The past is not erased. The black hole information paradox makes this point sharply. When a black hole forms from collapsing matter and then evaporates via Hawking radiation, what happens to the information that was in the infalling matter? Stephen Hawking's original calculation suggested that the Hawking radiation is thermal and contains no information, that the information is destroyed when the black hole evaporates, but this would violate unitarity. It would mean that quantum mechanics breaks down at the event horizon, that the Schrödinger equation does not apply to black holes, that the universe is not, after all, a closed unitary quantum system. Most physicists found this deeply unacceptable. The theoretical development of the past several decades, particularly work on ADS CFT correspondence, holography, and the more recent firewall debate and island formula calculations, has strongly indicated that black holes do not destroy information. The Hawking radiation does carry information, encoded in subtle correlations that are invisible in any low-order calculation, but are present in the exact quantum state of the radiation. Unitarity is preserved. Information is not lost. This is directly relevant to the question of the past. If even black holes do not destroy information, then ordinary physical processes certainly do not. The evolution of the universe does not erase its history. Every interaction that has ever occurred, every state the universe has ever been in, is preserved in the current quantum state of the universe, related to the present by a unitary transformation. The past exists not merely as a geometric feature of space-time, but as an informational feature of the quantum state of reality itself. The record is complete, the archive is intact, the information is all there, and yet you cannot read it. You cannot reconstruct your breakfast from the current quantum state of the universe, even in principle, because the calculation required is incomprehensibly more difficult than anything that could be physically implemented. The information is there, the access is gone, and the mechanism that took accessible information and made it inaccessible while preserving it has a name. It is called decoherence, and it is the next piece of the puzzle. Part 9. The hidden record problem. Decoherence is the process by which quantum systems lose their quantum coherence through interaction with their environment. When a quantum particle interacts with its surroundings, with air molecules, with photons, with the electromagnetic field, it becomes entangled with those surroundings. The quantum superpositions that characterize isolated quantum systems, the superpositions that make quantum mechanics strange and non-classical, spread out into the environment and become effectively unobservable, not because they disappear, because they become encoded in a vast, complex, highly entangled state that involves an astronomical number of environmental degrees of freedom. The superposition has not collapsed. The information has not been destroyed. It has been dispersed into the environment in such a way that recovering it would require simultaneously measuring all those environmental degrees of freedom with perfect precision, which is, in practice, completely impossible. This is the hidden record problem. The past is encoded in the quantum state of the universe. It is preserved by unitarity, but it has been scrambled through decoherence and thermalization into a form that is practically irretrievable. The information is like a message that has been translated into an alphabet of 10 to the power of 100 characters, each character encoded in the quantum state of a different particle somewhere in the universe. The message is still there, intact, technically recoverable. But the practical requirements for recovery are so far beyond anything physically realizable that the message is, for all practical purposes, gone. The holographic principle, which emerges from string theory and adds CFT, suggests that all the information in a volume of space-time can be encoded on its boundary. This is another piece of evidence that information is globally preserved even when locally inaccessible. The black hole scrambling time, the timescale over which information falling into a black hole gets maximally scrambled into the Hawking radiation, is an example of information that is preserved but effectively unreadable. The past of the universe is, in a sense, its own hologram, fully encoded in the present state, but requiring an unimaginably complex decoding process to read. So the picture that emerges from quantum mechanics, added to the block universe picture from relativity, is this. The past exists, fully and completely, in two separate senses. It exists as a set of real events at fixed space-time coordinates, unreachable by causal travel. And it exists as encoded information in the quantum state of the universe, unreadable because of the combinatorial impossibility of the decoding task. The past is not missing. It is hidden. And the hiding is done not by a law that says the past must be inaccessible, but by the combined effects of geometry and information scrambling. Which means the question of why you cannot go back is, at its most fundamental level, a question about geometry and information theory, not about time itself. Part 10. Entropy as information loss. There is a way of restating Boltzmann's entropy in terms of information that strips away any remaining sense that entropy is a physical force or a substance, and reveals it as something more fundamental and more strange. Claude Shannon, working in 1948 on the mathematical theory of communication, defined information entropy, a quantity he borrowed from thermodynamics but gave a new interpretation. Shannon entropy measures the uncertainty in a probability distribution. If you know the outcome of something exactly, the Shannon entropy is zero. There is no missing information, no uncertainty. If every outcome is equally possible, the Shannon entropy is maximum. You have as much uncertainty as possible. And the mathematical formula for Shannon entropy is identical to Boltzmann's formula for thermodynamic entropy up to a change of units. This is not a coincidence. It is a deep connection. What it tells us is that thermodynamic entropy is a measure of missing information. A high entropy state is a state about which you have very little microscopic information, even if you know the macroscopic properties. You know the temperature, the pressure, the volume, but you know almost nothing about the specific positions and velocities of the individual molecules. There are so many microstates consistent with the macroscopic description that specifying which one you're actually in would require an enormous amount of information. A low entropy state is a state about which you have more microscopic information, because fewer configurations are consistent with the macroscopic description. And now the arrow of time becomes something even stranger. Time's direction is the direction of increasing informational inaccessibility. As the universe evolves, the microscopic state becomes harder and harder to specify from macroscopic observations. More and more information about the microscopic past becomes scrambled into correlations that are, practically speaking, unobservable. The past is not erased by time's arrow. The past becomes harder and harder to read. The arrow of time is, in this interpretation, the direction of increasing ignorance, the direction in which the universe becomes less and less reconstructible from macroscopic observation. This is a profound reframing. It means that the irreversibility of time is not a feature of the universe's dynamics. It is a feature of the relationship between macroscopic observers, beings who can only access averaged, coarse-grained, macroscopic properties of the world, and the microscopic reality that underlies those properties. If you were a being who could observe and compute with every quantum degree of freedom of the universe simultaneously, if you were, in short, something like Laplace's demon, there would be no arrow of time. Every state would be equally accessible in both temporal directions. Unitarity guarantees it, but you are not Laplace's demon. You are a macroscopic object embedded in the universe, with access to a tiny, coarse-grained slice of its total information. And from your perspective, the universe's history is increasingly inaccessible as you look further into the past, not because the information is gone, because you cannot access it. Time's arrow is your epistemic limitation projected onto the cosmos. It is the universe's way of being more complicated than you are. Coarse graining, the process of averaging over microscopic details to get macroscopic descriptions, is where the irreversibility enters. When you describe the world in terms of temperature and pressure, rather than molecular positions and velocities, you are throwing away information. Every coarse-graining step discards details, and discarded details cannot be recovered, because you no longer know which microscopic state you are in. The universe still knows it retains the full microscopic state unitarily and exactly. But your description of the universe has lost that information, and since your causal future depends on your current macroscopic description, not on the full microscopic state, the information that has been coarse-grained away is causally irrelevant to your future, but causally connected to your past. This asymmetry, past information, was macroscopically accessible once, before coarse-graining, and future information is not yet macroscopically accessible, is what generates the felt asymmetry between past and future. The past feels different from the future because of the direction in which information flows relative to your macroscopic description of reality. Part 11. The observer problem. There is a connection between entropy, measurement, and time that was first made precise by Rolf Landauer in 1961, and it turns out to be one of the most illuminating links in the entire chain of reasoning about why time has a direction. Landauer's principle states that erasing one bit of information necessarily dissipates a minimum amount of energy as heat, specifically k times t times the logarithm of 2, where k is Boltzmann's constant and t is the temperature of the environment. This is the minimum thermodynamic cost of information erasure. It cannot be circumvented. It follows from the second law and from the fact that erasing information, reducing a system from multiple possible states to one definite state, decreases the entropy of the information-bearing system, and that decrease must be compensated by an entropy increase in the environment. The connection to the arrow of time is subtle but genuine. Observers interact with reality. Interactions leave records. Records are physical states that encode information about past events. Maintaining and updating those records, processing information, computing, measuring, necessarily involves thermodynamic processes that dissipate energy and increase entropy. An observer embedded in the universe generates entropy by the very act of observing, recording, and reasoning. The act of measuring a quantum system, for example, involves the amplification of a microscopic quantum event into a macroscopic, irreversible record. A track in a detector, a pointer deflection, a voltage threshold being crossed. That amplification process is irreversible and entropy generating. This suggests something remarkable. The arrow of time may not merely be observed by minds. It may be, in part, produced by them, or rather, by any physical process that acts as an observer, that amplifies microscopic events into macroscopic records, that coarse-grains reality and throws away microscopic information. Every record-creating process adds to the universe's entropy and therefore reinforces the thermodynamic arrow. The past is not only inaccessible because entropy has increased. The past is made inaccessible, in part, by the very processes that create records of it. The act of remembering contributes, in a tiny but real physical way, to the irreversibility of time. Experimental physics has made this connection between time and observation more concrete in recent decades. Ultra-precise atomic clocks, clocks accurate to a billionth of a second, have confirmed with extraordinary precision the predictions of both special and general relativity regarding time dilation. Time passes more slowly, in stronger gravitational fields, and at higher velocities. This has been confirmed not only for atomic clocks on satellites versus on the ground, but for clocks separated by as little as 33 centimeters in height. The physical variability of time's flow, the fact that time is not a universal clock ticking at the same rate everywhere, but a local geometric property of space-time that depends on local conditions, reinforces the picture of time as a feature of the observer's relationship to space-time, rather than an absolute background. The observer problem in quantum mechanics, meanwhile, remains genuinely unresolved. The measurement problem, the question of why quantum systems appear to take on definite values when measured, given that the Schrödinger equation predicts they should remain in superpositions, is connected to the emergence of classical, irreversible records from quantum, reversible dynamics. Every interpretation of quantum mechanics, Copenhagen, many worlds, pilot wave, relational, handles this connection differently. But all of them agree that the interface between quantum evolution and macroscopic observation is where the apparent irreversibility of measurement enters. And since memories and records are macroscopic observations, the arrow of time that organizes the past into an accessible record and the future into an open space of possibility is connected, at some level yet to be fully understood, to the process of quantum measurement and its apparently irreversible production of classical facts. Part 12. Multiple arrows, one direction. There is not one arrow of time in physics. There are several, and the fact that they all point in the same direction is itself a puzzle that has not been fully explained. The thermodynamic arrow is the one we have been discussing. Entropy increases toward the future. The cosmological arrow is the expansion of the universe, which also defines a temporal direction. The universe is larger in the future than in the past, and the expansion rate has varied in a directional way across cosmic history. The psychological arrow is the direction in which memory and consciousness operate. We remember the past and anticipate the future, not the reverse. The electromagnetic arrow is the one discussed earlier. Radiation propagates outward from sources rather than converging inward. And there is a fifth, much weaker arrow. The weak nuclear force is not perfectly time-symmetric. CP violation, the slight preference of certain weak interaction processes for one combination of charge conjugation and parity over another, has been observed experimentally, most famously in kaon decay. The violation is tiny, about 1 part in 1,000, and it is not clear how it relates to the macroscopic arrow of time, but it is there. The weak force knows, at some microscopic level, which direction is time. The alignment of all these arrows with each other, the fact that the direction of increasing entropy is the same as the direction of cosmological expansion, which is the same as the direction of psychological memory, which is the same as the direction of electromagnetic radiation, is not independently explained by any of them. Penrose and others have argued that the cosmological arrow and the thermodynamic arrow are deeply connected, both rooted in the low entropy initial state of the universe. The psychological arrow presumably follows from the thermodynamic arrow, since brains are thermodynamic systems that process information. The electromagnetic arrow is related to the thermodynamic arrow through the absorber theory of radiation. But the CP violation arrow has no clear connection to the others, and whether it plays any fundamental role in the macroscopic arrow remains unknown. The convergence of all these arrows on the same direction suggests either that they are all manifestations of a single underlying asymmetry, perhaps the past hypothesis, the low entropy initial condition, or that there is some organizing principle we have not yet identified. The fact that you cannot go back to the past is reinforced by all of these arrows simultaneously, which is part of why it feels so absolute. Not one, but many aspects of physics conspire to make the past a one-way door, and yet, underneath all of them, at the microscopic level, the laws are still time-symmetric. The conspiracy is pervasive, but its origin remains mysterious. Part 13. Wheeler-DeWitt equation. In the 1967 paper by John Wheeler and Bryce DeWitt, the attempt to quantize general relativity, to write down the quantum mechanics of space-time itself, produced an equation that has troubled physicists ever since, not because it is wrong, but because of something conspicuously absent from it. The Wheeler-DeWitt equation describes the quantum state of the universe. It takes the form of a constraint equation, the Hamiltonian of the universe, acting on the universal wave function equals 0. H acting on psi equals 0. This looks like Schrödinger's equation, the quantum equation of motion, but with a crucial difference. In the Schrödinger equation, the Hamiltonian acting on the state equals I times h bar times the partial derivative of the state with respect to time. Time appears explicitly. It is there, in the equation, as an independent variable, as the parameter with respect to which the state evolves. In the Wheeler-DeWitt equation, there is no time derivative. There is no time variable. The equation is timeless. The universal wave function does not evolve with respect to time, because in the Wheeler-DeWitt formalism, there is no external time for it to evolve with respect to. This is not a quirk or an artifact of the formalism. It reflects something deep about the structure of general relativity and quantum mechanics at the interface. In general relativity, there is no fixed background spacetime. Spacetime is dynamic. It evolves. It is part of the physical system being described. This means that time, in general relativity, is not a fixed external parameter, but a feature of the geometry that is itself dynamical. When you try to quantize this, when you try to write down quantum mechanics for a system that includes spacetime itself, you find that there is no external time left to serve as the evolution parameter. The universal wave function cannot evolve with respect to time because time is inside the system, not outside it. The result is what has been called the problem of time in quantum gravity. The Wheeler-DeWitt equation describes the universe as a static, timeless wave function. There is no change, no evolution, no arrow. The universe just is. All at once, frozen, a single static quantum state. But we manifestly experience time. We experience change, sequence, before and after. How does the experience of time emerge from a static, timeless wave function? One approach, developed by Don Page and William Wouters and extended by several others, is called relational time or timeless quantum mechanics. The idea is that time emerges from correlations within the universal wave function. Different subsystems of the universe are quantum mechanically correlated with each other. When you describe the state of one subsystem, say a clock, you find that its state is correlated with the state of another subsystem, say a particle. When the clock reads 1 second, the particle is here. When the clock reads 2 seconds, the particle is there. These correlations create the appearance of temporal evolution of the particle moving through time, even though the universal wave function itself is timeless. Time is not fundamental. Time is relational. It emerges from the structure of entanglement within a static quantum state. This is a direct, concrete manifestation of the idea that the past still exists. If the universal wave function is timeless and static, then every moment, every slice of experienced time is encoded in it simultaneously. Your breakfast and your birth and this moment and your death are all correlated states of subsystems within the same static wave function. None is more now than any other. The apparent flow from past to future is the experience of navigating the correlation structure of a wave function that contains everything at once. The past does not need to be preserved because it was never the past in the sense of something that came before and was then lost. It is simply a different correlation structure within the same timeless whole. This does not make the past accessible. The correlation structure that corresponds to your breakfast is still encoded in the wave function in a way that you, as a macroscopic observer embedded in the universe, cannot access from your current position in the correlation network. But it does mean that the past's existence is not a matter of preservation. It is a matter of eternal co-presence within a timeless structure. Everything has always been there. Everything always will be there. The question of whether you can reach the past is the question of whether you can navigate to a different region of a static wave function, and the dynamics of that navigation, whatever they are, do not permit the journey. Part 14. Barber's Timeless Landscape. Julian Barber is a British physicist who has spent decades thinking about time, and he has arrived at a view that takes the Wheeler-DeWitt equation seriously in a way that most physicists have been reluctant to do. Barber's framework begins with a mathematical space he calls Platonia, not the philosopher's Plato, but the place of Platonic forms, the place where all possible configurations of the universe exist simultaneously as abstract objects. Platonia is the space of all possible three-dimensional configurations of all the matter in the universe. Every possible arrangement of every possible particle is a point in Platonia. The universe, in Barber's picture, does not move through time. There is no trajectory through Platonia. Each point in Platonia simply exists, timelessly, as a possible configuration of reality. The Wheeler-DeWitt equation assigns a quantum amplitude, a number that determines the probability of a configuration being experienced to each point in Platonia. The configurations with high amplitude are the ones that are likely to be observed. The configurations with low amplitude are the ones that almost never occur. The key move is this. The configurations in Platonia that have high amplitude are, in Barber's analysis, configurations that contain what he calls time capsules. A time capsule is a configuration that encodes a record of an apparent history. Your brain, at this moment, is a configuration that contains memories, physical structures that encode, in their current arrangement, what appears to be a past sequence of events. A geological rock layer is a configuration that contains strata, physical structures that encode what appears to be a temporal sequence of deposition. The fossil record is a time capsule. Light from distant galaxies is a time capsule. Everything you interpret as evidence of the past is, in Barber's framework, a feature of the present configuration, a structural pattern within the current point in Platonia. In Barber's picture, there is no past. There is no trajectory from past configurations to the present configuration. There is only the present configuration, and within it, the physical structures that we interpret as memories and records. The experience of time flowing, the sensation that you were just at your breakfast table, and before that you were asleep, and before that you were alive in the past, is entirely a feature of the current configuration of your brain. The memories that constitute your apparent history are real, physical structures in your neurons right now. They were built by processes that occurred in prior configurations of reality, yes, but those prior configurations do not stand in a causal temporal relationship to the present configuration in the sense of having caused it through a sequence of steps. They are simply other points in Platonia, with their own amplitudes, their own existence as timeless configurations. The inaccessibility of the past, in Barber's framework, is total but also somehow trivially true. You cannot access the past because there is no access mechanism, not because some law prevents the access, but because access between configurations is not a concept that applies in a timeless universe. Configurations do not communicate. They do not pass information. Each one is entirely self-contained. The past does not need to be sealed off because there is no pathway between configurations to be sealed off in the first place. The past is not an inaccessible location. It is a different configuration that simply is without connection, without a passage that could be travelled in either direction. And yet here is what makes Barber's picture connect so directly to the central question. The configurations that we experience, the ones with high amplitude, the ones that are likely to be observed, are precisely the ones that look like they have histories. They contain time capsules. They are structured in ways that make them look like they emerged from prior configurations. The low entropy early universe is encoded as a time capsule in the current configuration of the cosmic microwave background. The evolutionary history of life on Earth is encoded in the current configuration of the fossil record and the genome. Your personal history is encoded in the current configuration of your neural connections. The past exists, completely and permanently, as a set of real configurations in Platonia with their own quantum amplitudes. And it is encoded in the present as a set of structural imprints. But there is no passage from here to there, not because a law prevents it, because passage is not a feature of timeless existence. This is the most radical version of the answer to the question, why can't we go back? In Barber's universe, the question is not quite right. There is no going back because there is no going at all. There is only the eternal coexistence of all configurations, and within each configuration, the internal structure that makes it look like it has a history. You cannot go back to your breakfast because going presupposes time, and time presupposes something Barber believes is an illusion built from the inside of a static configuration. The past feels inaccessible because it is structurally encoded in the present rather than causally continuous with it. You are not separated from your past by a passage of time. You are separated from it by a transformation between configurations that has no inverse in any accessible physical process. And that separation is complete, absolute, and, in a strange way, as fundamental as physics gets. Part Quindici, Rovelli's thermal time. Carlo Rovelli is one of the founders of loop quantum gravity, one of the 2 or 3 most serious candidates for a complete theory of quantum spacetime, and he is also, by any reasonable measure, one of the most philosophically articulate physicists alive. He writes books that non-physicists actually read and finish. He thinks carefully about what the equations mean, not just whether they work. And he has spent a significant portion of his career thinking about time, not just calculating with it, but asking what it actually is, whether it exists in any fundamental sense, and why it feels the way it feels from the inside of a conscious, thermodynamic, irreversible human life. His answer is called the thermal time hypothesis, and it is one of the more quietly radical ideas in contemporary theoretical physics. Not radical in the sense of being disconnected from the mathematics. It is grounded in rigorous formalism. Radical in the sense that it takes seriously a conclusion that most physicists prefer to leave implicit, that time, as you experience it, is not written into the fundamental laws of the universe. It is something the universe generates locally, under specific conditions, for observers who happen to find themselves embedded in a particular kind of thermodynamic situation, which, as it turns out, is exactly the situation you are in. Here is the core of the idea. In standard physics, time is a parameter. It is the variable you plug into your equations to describe how things evolve. You have a state at time 0, you apply the equations of motion, and you get the state at time 1, time 2, time 3. Time is the scaffolding on which the physics hangs. It is external to the system. It is, in a sense, assumed before the physics even begins. And in most situations, in a laboratory, in everyday life, even in special and general relativity, where time is flexible and observer-dependent, this works perfectly well. You have a clock, the clock ticks, you measure intervals, and the physics proceeds. But Ravelli, working in the framework of quantum gravity and taking the Wheeler-DeWitt equation seriously, noticed something that this picture obscures. When you write down the quantum mechanics of the universe as a whole, when the system you are describing is everything, not just a particle inside a box, there is no external time left. The universe has no outside. There is no clock that is not itself part of the system being described. The Wheeler-DeWitt equation, as we discussed earlier, is timeless. It describes the universe as a static wave function with no evolution parameter, no ticking clock, no external scaffolding. And yet here we are, experiencing time. So where does it come from? Ravelli's answer begins with a mathematical fact about quantum systems in thermal equilibrium. When a quantum system is in a thermal state, when it has settled into the kind of statistical distribution that characterizes a system at a definite temperature, the kind of state described by what physicists call the KMS condition, named after Kubo, Martin, and Schwinger, there is a natural one-parameter group of transformations generated by the system's Hamiltonian. This group of transformations has exactly the mathematical structure of time evolution. It defines a flow through the space of states. It has a direction. It organizes the observables of the system into a sequence that looks, from the inside, exactly like temporal succession. Ravelli calls this the thermal time, and his proposal is not merely that this flow resembles time. His proposal is that this flow is time, that what we experience as the passage of time, the before and after, the direction from past to future, is precisely and exactly this thermal flow. Time is not something the universe runs on. Time is something that emerges when matter reaches a thermal state and generates, through its statistical structure, a natural internal clock. The ticking you feel is not the universe's clock. It is your clock. It is the thermodynamic clock of your particular patch of reality, defined by the particular thermal state you and your environment happen to be in. This reframes the experience of time in a way that takes some sitting with. You are a warm, metabolizing, entropy-generating biological system embedded in a universe that is itself far from thermal equilibrium, sitting in the long, slow slide from the extraordinarily low entropy beginning toward whatever maximum entropy future awaits. Your thermal time is defined by the thermodynamic structure of your local environment, the temperature of your body, the chemical gradients driving your metabolism, the statistical state of the matter around you. That structure defines a flow. That flow is what you call now, and before, and after. It is not a universal backdrop against which events occur. It is a local, physical, emergent property of the specific material situation you find yourself in. The philosophical implications are significant. It means there is no universal now. It means that two observers in sufficiently different thermodynamic states could, in principle, experience thermal times that flow differently, not just at different rates, in the way that relativistic time dilation makes clocks tick differently at different velocities or gravitational potentials, but potentially in different directions. In principle, in a universe with very different thermodynamic structure, two observers could disagree not just about the rate of time, but about its direction, about which way is future and which way is past. The arrow of time is not a universal arrow etched into the cosmos. It is a local arrow defined by local thermodynamics, shared among all macroscopic observers in our universe, only because we all happen to inhabit the same global thermodynamic context, the same long entropy gradient that traces back to the same improbable beginning. In practice, this means that every macroscopic observer in the observable universe experiences the same direction of thermal time, because we are all embedded in the same thermodynamic situation. We all inherit our temporal direction from the same cosmic initial condition. The gradient runs the same way for all of us, from the low entropy past toward the high entropy future, and so our thermal times all point the same direction, and we all agree about what happened before and what comes after. But that agreement is not fundamental. It is contingent. It is a consequence of the shared thermodynamic heritage that every structure in the observable universe has inherited from the Big Bang. And this is precisely where Ravelli's picture reconnects to the central question that has been running through everything we have discussed. The past is inaccessible to you not because a law forbids the journey. The past is inaccessible because your thermal time points away from it. The direction you experience as the future, the direction in which your thermal flow runs, the direction in which your entropy increases, the direction in which your memories accumulate and your coffee cools and your body ages, is by definition the direction away from the past. The past is not behind a locked door. The past is in the direction opposite to the only direction your thermal time knows how to flow. You are not blocked from reaching it by a prohibition. You are pointed away from it by the thermodynamic structure of your own existence. And that thermodynamic structure, the one that defines your thermal time, that gives you your arrow, that makes the past feel sealed and the future feel open, is itself a consequence of the initial condition of the universe. The extraordinarily low entropy of the beginning created the gradient. The gradient created the thermodynamic structure. The thermodynamic structure created your thermal time. Your thermal time created your experience of before and after. The inaccessibility of the past is, when you follow the chain all the way down, rooted once again in that single, unexplained, improbably precise starting point. Ravelli's picture does not escape the mystery. No picture does. It traces the same thread back to the same knot. The knot is the beginning, and the beginning, as we have now seen from every direction physics can approach it, remains stubbornly, magnificently, and perhaps permanently unexplained. Part 16. Retrocausality and quantum loops. There is a class of quantum experiments that should make you genuinely uncomfortable if you believe that time has a simple, unambiguous, strictly forward direction at the microscopic level. Not uncomfortable in a vague philosophical way, uncomfortable in the specific way you feel when a result comes back from a laboratory and the result is saying something that your entire intuitive model of cause and effect cannot accommodate. These experiments have been run, the results are real, and what they suggest about the relationship between past and future at the quantum level is one of the most quietly destabilizing things in all of contemporary physics. Let us build it up carefully, because the setup matters enormously here, and it is easy to miss what is actually strange about it if you move too fast. You fire a photon toward a barrier with 2 slits in it. On the other side of the barrier is a detector screen. If you fire many photons one at a time and do nothing else, you get an interference pattern on the screen, a series of alternating bright and dark bands that can only be explained if each photon travels through both slits simultaneously as a wave interfering with itself. This is standard quantum mechanics. The photon is in a superposition of going through slit 1 and going through slit 2. The interference pattern is the physical signature of that superposition. Now you add a device that tags each photon with information about which slit it went through. It does not block any photons. It does not change their trajectories in any dramatic way. It simply records which path information, a label essentially, attached to each photon as it passes through. and the interference pattern vanishes completely. The photons now land on the screen in a distribution that looks like two overlapping blobs, one from each slit, with no interference bands. By acquiring information about which path the photon took, you have destroyed the superposition. The photon is no longer both paths at once. It is one path. The quantum coherence is gone. This much is familiar to anyone who has studied quantum mechanics. Measurement destroys superposition. Knowing which path the photon took is incompatible with the photon being on both paths simultaneously. Fine, that is strange enough on its own. But now comes the part that breaks the straightforward story of time. You can, after the photon has already hit the detector screen and been recorded, erase the which path information. You set up the experiment so that the path tagging device sends the which path information to a secondary detector, and you arrange things so that you have the option, after the photon has already landed on the main screen, to either read the which path information or destroy it, erase it without ever looking at it. And here is what happens. When you choose to erase the which path information, the interference pattern returns. Not in all the detected photons, but in a specific subset of them, the ones whose which path information was erased. When you sort the results using the information from the secondary detector, the interference is back, the superposition behavior is restored. Let that land for a moment. The photon hit the main detector. It landed somewhere. Its position was recorded. And then, afterward, a choice was made about information that existed at the time the photon was traveling, and that choice retroactively determined whether the photon's landing pattern shows interference or not. The future measurement, performed after the photon's journey was already complete, appears to have reached back and changed the character of what the photon did in the past. Now, there are careful and important caveats here, and they matter. You cannot use this to send a signal backward in time. You cannot use it to change the past in any way that a macroscopic observer could exploit to violate causality. The interference pattern only appears when you sort the results using information from the secondary detector, which means you need the secondary detector's data that is generated at the same time as or after the main detection event to see it. You cannot know just by looking at the main detector alone whether a given photon's which path information was later erased or not. The no-signaling theorems are safe. Causality at the macroscopic level is not violated, but the philosophical implication is not nothing. Because the standard story of quantum mechanics, the story where a quantum system has a state, the state evolves forward in time, and measurements reveal properties that existed at the moment of measurement, does not comfortably accommodate these results. The delayed choice quantum eraser is not saying that the future sends a signal to the past. It is saying something subtler and in some ways stranger, that the past behavior of a quantum system is not fully defined until the future measurement context is established. The photon's history, whether it behaved as a wave or as a particle during its journey, is not simply a fact that was settled when the photon was in flight. It is a fact whose character depends on what happens later. Past and future are entangled in a way that simple forward-in-time causality does not capture. Yakir Aharonov, one of the most creative and unconventional thinkers in quantum foundations, took these results seriously enough to build an entire reformulation of quantum mechanics around them. His two-state vector formalism proposes that a quantum system at any given moment is not described by a single state vector propagating forward from the past, the standard picture, but by two state vectors simultaneously. One propagates forward from the past boundary condition, as usual. The other propagates backward from the future boundary condition. The observable properties of the system, at any moment, are determined by both vectors together, by both the past and the future, simultaneously. This is a time-symmetric formulation of quantum mechanics, and it is mathematically rigorous and internally consistent. It is not a fringe speculation. Aharonov has been working on it for decades. it has generated a substantial body of experimental predictions, and some of those predictions have been confirmed through the framework of weak measurements, a technique that allows you to extract partial information from a quantum system without fully collapsing its state. The two-state vector formalism naturally and elegantly accommodates the delayed choice quantum eraser results, because in that formalism, the past and future boundary conditions are on equal footing. Of course, the future measurement affects the apparent past behavior of the photon. The future boundary condition was always part of the description. The formalism does not require full retrocausality in the dramatic sense. It does not require that future events send detectable signals backward in time, that effects precede causes in any way a macroscopic observer could notice or exploit. It is fully consistent with the no-signaling theorems, but it does suggest something important, that the asymmetry between past and future that we experience macroscopically, the asymmetry that makes causes come before effects, that makes the past feel fixed and the future feel open, that makes the broken egg irreversible and the future unwritten, may not be present at the microscopic quantum level in the way we usually assume. At the quantum level, the past and the future may be more symmetric than they appear. The macroscopic arrow of time may be emerging from something that, at its foundation, does not have a preferred direction at all. This connects to a broader set of ideas in cosmology about whether the universe has not just a low entropy initial condition, the past hypothesis, but potentially a corresponding future condition as well. Thomas Gold proposed in 1958 a model in which the universe has low entropy at both temporal ends, implying that the arrow of time would reverse in the far future as the universe eventually collapsed back in on itself. In the early phase, entropy would increase toward what we call the future. In the late collapsing phase, entropy would increase toward what was previously the past. Two arrows pointing at each other from opposite ends of cosmic history, meeting somewhere in the middle. This model has been largely set aside. The observational evidence now strongly favors a universe that expands forever rather than eventually collapsing, making a low entropy future boundary condition physically unmotivated. But the conceptual possibility of two boundary cosmologies, of a universe symmetric in time at the largest scales, remains alive in some approaches to quantum gravity. Sean Carroll and Jennifer Chen took a different approach, proposing a cosmological model in which time's arrow emerges not from a single special initial condition imposed by fiat, but from the statistical behavior of quantum fluctuations in a de Sitter space, the kind of space-time geometry associated with a universe dominated by a cosmological constant, like the one we appear to live in. In their model, the larger space-time structure has no global arrow of time. It is symmetric, but within it, low-entropy regions form spontaneously through quantum fluctuations and then undergo inflationary expansion, producing local universes, like ours, in which entropy increases in a locally defined direction that the inhabitants of that region experience as the future. Our arrow of time is not universal, it is local. It is the arrow of our particular bubble of low entropy in a larger, directionless space-time foam. Other bubbles could have arrows pointing in any direction. We simply cannot see them. None of these approaches has fully succeeded. The quantum eraser results and the two-state vector formalism suggest that at the microscopic level, time may be more symmetric than our macroscopic experience suggests. Retrocausal interpretations remain minority positions in the physics community, but they are mathematically consistent, experimentally grounded in the sense that the experiments they describe are real and not ruled out by any confirmed observation. The question of whether causality, the principle that causes strictly and always precede their effects, is a fundamental law of nature or an emergent statistical regularity that arises from asymmetric initial conditions, is genuinely open. It has not been settled. And that means the question of why the past is unreachable includes, as a live and legitimate possibility, the idea that at the deepest level, the past and future are not as different as they seem. That the asymmetry you feel in every moment of your life, the sealed past, the open future, the one-way door, is not written into the bedrock of reality. It is something that emerged, something that was generated, something that the universe produces under specific conditions from laws that do not, themselves, require it. And if it was generated, the question naturally follows, could it, under different conditions, be otherwise? That question does not yet have an answer. But the fact that it can be asked at all, seriously, by serious physicists, with serious mathematics behind it, should tell you something about how strange the foundations of time actually are. Part 17. The Missing Principle. Let us be honest about where physics actually stands. Not where the textbooks present it as standing, with their clean derivations and their confident arrows pointing from cause to effect, from past to future, from low entropy to high. Not where the popular science articles leave it, with their reassuring sense that the big questions are mostly settled and the remaining gaps are technical details being mopped up by graduate students. Where it actually stands. Because the actual situation, when you look at it directly, is that one of the most familiar features of reality, the fact that time has a direction, that the past is sealed and the future is open, that you can remember yesterday but not tomorrow, has no complete explanation. Not an incomplete one that is getting there. Not a provisional one pending a few more experiments. No complete explanation. And every framework that has tried to provide one has, without exception, relocated the mystery rather than resolved it. Start with statistical mechanics. Boltzmann's achievement was genuine and extraordinary. He took the reversible microscopic laws of classical mechanics and showed, with mathematical rigor, why macroscopic systems evolved toward higher entropy states. He gave us the connection between the microscopic world of atoms and the macroscopic world of temperature and pressure and heat flow. He built the framework that underlies virtually all of modern thermodynamics and chemistry and materials science. But his account of entropy, increase, the account that is supposed to explain why time runs forward, why the broken egg does not reassemble, why coffee cools and never spontaneously heats, requires as an input a fact that the theory cannot derive. It requires that the universe started in a state of very low entropy. Without that initial condition, the statistical argument for entropy increase does not give you a preferred direction. It gives you a universe equally likely to evolve toward higher entropy in either temporal direction, which is no arrow at all. The past hypothesis, David Albert's name for the assumption that the early universe had extraordinarily low entropy, is not a result of statistical mechanics. It is a boundary condition inserted into statistical mechanics from outside, because without it the theory gives the wrong answer. The mystery of time's direction has been relocated from the dynamics of physical systems to the initial state of the universe. The question, why does time have a direction, has become, why did the universe start the way it did? That is progress of a kind. It is a more precise question, but it is not an answer. Then comes inflation, which looks at that more precise question and makes a serious attempt to answer it. Alan Guth's proposal that the very early universe underwent a period of exponential expansion driven by a scalar field called the inflaton accounts for the smoothness and flatness and large-scale structure of the universe in ways that had previously required even more extreme fine-tuning. Inflation is a genuine achievement. The predictions it makes about the pattern of fluctuations in the cosmic microwave background have been confirmed observationally with impressive precision. It is the best cosmological framework we have for describing the universe's earliest moments. But Guth himself has said explicitly, not as a criticism of his own theory, but as an honest accounting of what it does and does not do, that inflation does not solve the entropy problem. What inflation does is trade one fine-tuned initial condition for another. Instead of a fine-tuned initial state of the entire universe, you now need a fine-tuned initial state of the inflaton field a configuration that would trigger the exponential expansion in the right way to produce the universe we observe. The entropy problem has been pushed one step earlier in the timeline to a pre-inflationary regime about which our theoretical knowledge is even thinner and our observational leverage is essentially zero. The mystery has moved. It has not disappeared. It is now sitting in a period of cosmic history that we cannot directly probe and for which we have no confirmed theoretical framework. Inflation shifts the question from the Big Bang to whatever came before inflation, which is, if anything, a harder question. Quantum mechanics enters the story with a different kind of contribution. The Schrödinger equation, with its unitary evolution, gives us a precise and rigorous account of why the past is informationally preserved. As we have discussed at length, unitary evolution conserves all information about prior states. The quantum state of the universe today is related to every prior quantum state by a transformation that is in principle invertible. Nothing is erased. The past is encoded completely and permanently in the current quantum state of reality. This is a profound and important result, but it does not explain why the past is inaccessible. Knowing that the information is there does not tell you why you cannot read it. The scrambling of quantum information through decoherence and thermalization explains the practical unreadability of the past. The information has been dispersed into correlations involving so many degrees of freedom that reconstruction is computationally impossible. But decoherence and thermalization run in the direction they run because of the initial conditions. The scrambling proceeds forward in time rather than backward in time, because the universe started in a low entropy state that makes forward scrambling overwhelmingly more probable than backward unscrambling. Quantum mechanics, in other words, preserves the past and explains why it is unreadable, but cannot explain why the unreadability is directed the way it is. It defers to thermodynamics for the direction. Thermodynamics defers to the initial condition. The initial condition is unexplained. The chain of deferral is intact. The timeless approaches, Wheeler-DeWitt, Barber's Platonia, the relational interpretations of quantum gravity, take a more radical step. They dissolve the problem, in a sense, by removing time from the fundamental description of reality entirely. If there is no fundamental time, there is no fundamental arrow of time, and therefore no arrow to explain. The problem disappears. But it disappears by being replaced by a different and arguably harder problem, explaining how experienced time, time with a direction, time with a past that feels sealed and a future that feels open, time that underlies memory and anticipation, and the entire phenomenology of conscious experience emerges from a timeless wave function, and that explanation does not exist in any complete form. We have sketches, we have proposals, we have the Page-Wouters relational time mechanism, which shows how temporal correlations can emerge from a static wave function through entanglement between subsystems. We have Barber's time capsules, which show how configurations containing apparent histories can be selected by the amplitude structure of the universal wave function. These are genuine ideas with genuine mathematical content, but none of them fully explains why the experienced time that emerges from the timeless foundation has the particular properties it has, why it has an arrow, why it feels one-directional, why the configurations with high amplitude are specifically the ones that look like they have histories pointing in one temporal direction rather than both or neither. The emergence of directed experience time from timeless physics is not understood. The problem has been dissolved in name and relocated in substance. Ravelli's thermal time, as we have just explored, gives perhaps the most precise and philosophically satisfying account of what time actually is for real observers embedded in real thermodynamic situations. Time is the thermal flow generated by the statistical state of the observer's environment. It is local, emergent, tied to entropy, but it too defers to thermodynamics for the direction of that flow. It does not explain why the thermodynamic structure of the universe points the way it does. It does not explain why your thermal time runs from lower entropy to higher entropy rather than the other way. It inherits its direction from the global thermodynamic context, which inherits its direction from the initial condition, which remains unexplained. Ravelli has relocated the mystery with extraordinary elegance. The mystery is still there. Every framework does the same thing. Boltzmann shifts the question from dynamics to initial conditions. Inflation shifts it from the Big Bang to the pre-inflationary state. Quantum information theory shifts it from thermodynamics to the scrambling of entanglement. Timeless quantum mechanics shifts it from temporal flow to the amplitude structure of configuration space. Thermal time shifts it from universal time to local thermodynamic context. Each shift is genuine progress. Each shift makes the question more precise, more mathematical, more connected to other deep questions in physics. But no shift has found the bottom. No framework has arrived at a level where the question, why does time have a direction, is answered without immediately generating a new version of the same question one level down. This is not, to be clear, a failure of individual physicists or individual theories. The people working on these problems are among the most capable scientists alive, working with the most powerful mathematical tools ever developed on the most precisely tested physical theories in history. The fact that they have not solved this problem is not a reflection on them. It may be a reflection on the problem. It may be telling us something about the nature of the question itself, that it is pointing at a gap in the conceptual framework of physics that cannot be filled by any currently existing concept. That what is needed is not a better calculation within the existing frameworks, but a genuinely new principle, a new way of thinking about the relationship between time and physical law that does not yet exist and whose shape we cannot currently discern. Some physicists believe that the completion of quantum gravity, a theory that successfully merges quantum mechanics and general relativity in a way that is consistent and empirically adequate, will finally reveal why time has a direction, that the origin of time's arrow is somehow bound up with the quantum nature of spacetime at the Planck scale, and that understanding spacetime at that scale will explain why the macroscopic arrow points the way it does. Others believe the answer lies in understanding the cosmological boundary conditions of the universe at a deeper level, in a quantum gravity theory of the Big Bang that derives the past hypothesis rather than assuming it. That explains from first principles why the universe began in a state of such extraordinary low entropy. Others believe the answer lies in a proper resolution of the quantum measurement problem, that understanding why quantum superpositions give way to classical definite outcomes will clarify why time seems to flow, why the past is fixed and the future is open, why measurement is irreversible, even though the underlying quantum dynamics is reversible. What is clear, beyond any reasonable dispute, is that no such explanation currently exists. Physics can tell you, with extraordinary precision and confidence, that the past is real, preserved, encoded, geometrically permanent, informationally intact. Physics can describe every mechanism by which the past is made inaccessible. Physics can trace the chain of deferral from thermodynamics to initial conditions to quantum gravity and back. What physics cannot do, what it has not been able to do in 150 years of serious, rigorous, mathematically sophisticated effort, is tell you why all those mechanisms conspire to point in the same direction, why the initial condition was special, why the universe began the way it began, why, given that every fundamental law permits both directions, reality insists on only one. There is no law that says time must flow forward. There is only the accumulated weight of a century and a half of failed attempts to derive such a law, the growing suspicion that no such law exists, and the slowly clarifying sense that the answer, when it finally comes, will require a principle we do not yet have, at a level we have not yet reached, connecting quantum mechanics and gravity and information and entropy in a way that no existing framework has managed. That level has not been reached. That principle has not been found. And until it is, every answer to the question of why you cannot go back to the past is, in the most precise and honest sense possible, incomplete. Part 18. The final realization: the past still exists. Come back to the morning, the cup of coffee, whatever temperature it was when you first picked it up, the specific arrangement of molecules in the ceramic and the water and the dissolved compounds, the exact pattern of steam rising from the surface, the photons that scattered off that surface and travelled the short distance to your eyes, each one carrying information about colour and brightness and the particular quality of the light in the room at that moment, the electrical signals that those photons triggered in your optic nerves, the cascade of neural activity in your brain as it processed all of that sensory information, built a model of the scene, filed it into the ongoing narrative of your morning. All of that, every particle, every field, every quantum state involved in that entirely ordinary, entirely forgettable moment, was real. It happened. And according to the best physics we have, according to the most precisely tested theoretical frameworks in the history of science, none of it has been unmade. Not one particle of it. Not one bit of information. Not one quantum correlation. The morning is gone in the only sense that matters to you, the sense of being accessible, of being reachable, of being something you could return to. But in the sense that matters to physics, it is still there, completely, permanently, exactly as it was. The block universe is not a metaphor or a poetic way of talking about the past. It is the mathematical structure of space-time, as described by general relativity, the most precisely tested theory in the history of science, a theory confirmed by GPS satellites that would drift by kilometers per day without relativistic corrections, confirmed by gravitational wave detectors that measure distortions in space-time geometry smaller than 1,000th of the diameter of a proton, confirmed by the orbits of planets, the bending of starlight around the sun, the precession of pulsars, the expansion history of the universe. General relativity's description of space-time as a four-dimensional geometric structure in which time is one coordinate among four, in which every event has a fixed location in the space-time manifold, in which the distinction between past, present, and future is observer-dependent rather than absolute, is not an interpretation or a philosophy. It is the mathematical content of a theory that has passed every experimental test ever devised for it. And in that structure, the space-time coordinates of your morning cup of coffee are exactly as real as your current space-time coordinates. The event exists at its location in the four-dimensional manifold. It is fixed there. It is permanent. It is, in the precise technical sense of general relativity, as real as you are right now. You simply cannot travel to it, for the same geometric reason that you cannot travel to a point in space that is not where you are without moving through the intervening distance. And the physics of how massive objects move through space-time does not permit travel backward along the time direction. Not because a law forbids it with some explicit prohibition, because the geometry of the space-time manifold, combined with the constraint that massive objects must follow time-like paths and cannot exceed the speed of light, makes backward temporal trajectories geometrically unavailable. The room is there. The door opens only one way. The quantum state of the universe is not a metaphor either. It is a precise mathematical object, the wave function, described by the Schrödinger equation and its relativistic generalizations, the object that has been confirmed to describe the behavior of quantum systems with extraordinary precision across every physical domain we can probe, from single electrons to superconducting circuits involving billions of particles behaving coherently. That object evolves unitarily. Unitarity is not an approximation or an assumption. It is a provable mathematical property of the Schrödinger equation, with provable consequences for information conservation. A unitary transformation is reversible. It preserves all information. It maps states to states in a way that loses nothing and destroys nothing. The information content of your morning, the quantum state that encoded your coffee and your kitchen and your body and the air in the room at that specific moment, has not been deleted by the passage of time. It has been scrambled. It has been dispersed through the process of decoherence and thermalization into the quantum entanglement structure of an almost incomprehensibly large number of degrees of freedom spread across the observable universe. Somewhere in the correlations between the positions and momenta of particles throughout the cosmos, the quantum fingerprint of your morning persists, encoded in a form that is in principle reconstructible. If you had the ability to measure every relevant degree of freedom simultaneously and perform the inverse unitary transformation on the result, you do not have that ability. No physical system that could exist within the universe could have that ability. The computational resources required exceed anything that could be physically instantiated within the known cosmos. But the information is there. The record is intact. The universe has not forgotten your morning. It has simply filed it in a location that nothing can reach. Entropy has not erased the past. This is the distinction that matters more than any other in this entire discussion, and it is worth stating as plainly as possible. Entropy has made the past computationally inaccessible. Those are completely different things, and conflating them is the source of most of the confusion about what the arrow of time actually means. Think about the difference this way. A book that has been burned is destroyed. The information it contained, the specific sequence of words, the ideas encoded in their arrangement, is gone. The second law of thermodynamics, applied to the burning process, tells you that the entropy of the system increased and that the information in the book has been irreversibly dispersed into heat and ash and smoke in a form from which it cannot be reconstructed. The book is gone. But now consider a different scenario. A book that has been translated, character by character, into a cipher so complex that no computer that could be built within the observable universe could crack it in a time shorter than the current age of the universe. That book still exists. The information is completely intact. Every word, every sentence, every idea is preserved in the cipher, exactly and completely. You just cannot read it. Not because the information is missing, but because the decoding task exceeds any available computational resource. The past is the second kind of book, not burned. Encoded in a cipher of cosmic complexity, a cipher written in the language of quantum entanglement and thermodynamic correlations, a cipher whose key would require measuring and processing every quantum degree of freedom of the observable universe simultaneously. The morning is there. You just cannot read it back. Going back is structurally forbidden, and here it is important to be precise about what structurally forbidden means, because it is not the same as prohibited by a law. There is no law of physics that says the past must be inaccessible. There is no equation in Newton or Maxwell or Einstein or Schrödinger that contains an explicit prohibition on backward temporal travel or on entropy decrease. What there is, instead, is a combination of structural features of reality that together make the past unreachable without making it unreal. Space-time geometry makes backward temporal trajectories unavailable to massive objects. The thermodynamic arrow, rooted in the extraordinarily low entropy initial condition of the universe, points with overwhelming probabilistic force away from the past toward the future. The informational scrambling of decoherence has dispersed the microscopic record of the past into an entanglement structure that exceeds any reconstructive capacity. And the relational structure of time itself, the possibility, suggested by Wheeler-DeWitt and Barber and the Page-Wouters mechanism, that time is not fundamental but emergent from correlations within a timeless wave function, means that the very concept of going back may rest on a misunderstanding of what time is at the deepest level. All of these work together. All of them conspire from different directions and through different mechanisms to make the past unreachable. None of them makes it unreal. The conspiracy is total. The room is locked. The room is still there. And here is the thing that sits at the center of all of this, the thing that should quietly shift how you relate to every moment as it passes through you and becomes the past. Every moment, as it passes, does not disappear. It becomes fixed. Before a moment arrives, it is part of the future, open, probabilistic, undetermined, not yet real in any definite sense. But the instant a moment passes, something happens to it that is the opposite of disappearance. It becomes permanent. It acquires a kind of reality that the future does not have and the present only briefly holds. It becomes a fixed event at fixed space-time coordinates, real in the geometry of the four-dimensional manifold. It becomes a contribution to the quantum state of the universe, encoded in the entanglement structure of reality with perfect fidelity. It becomes, in Barber's language, a configuration in Platonia, a point in the space of all possible arrangements of matter, existing timelessly alongside every other configuration, assigned its amplitude by the universal wave function. The past is not the realm of the lost. It is the realm of the permanently fixed. It is, in the most rigorous physical sense, the only part of time whose existence is completely guaranteed. The future might not happen the way you expect. The present is a knife edge of becoming. But the past, every moment of the past, including this one, the moment you are in right now, which is becoming past as you experience it, is real in a way that nothing else quite is. You cannot go back. The thermodynamic arrow forbids the journey with a force proportional to the improbability of the universe's beginning. The geometry of space-time closes off the trajectory. The scrambling of quantum information has made the route computationally impassable beyond any conceivable technology. The framework of emergent time suggests there may be no there to go back to in the way you imagine it, only configurations that contain within them the traces, the records, the time capsules of what was, written into the structure of matter by the processes that connect one moment to the next. But the past is not nothing. It is not absence. It is not loss in any physical sense. It is presence of a different kind, a permanent, indestructible, geometrically fixed presence that the laws of physics have never touched with an eraser. Everything you have experienced is encoded in the structure of the universe. Every conversation, every ordinary morning, every moment you thought was gone, each one is a real event at a real location in space-time, as present as the present in any deep physical accounting. The universe kept every receipt. It filed every record. It lost nothing. It simply put everything somewhere you cannot go. What physics cannot tell you, what it has been working on for 150 years without arriving at a complete answer, is why. Why are all the mechanisms pointing the same direction? Why was the initial condition so extraordinarily, implausibly special? Why does the block universe have the particular geometry it has, with time running the way it runs, rather than the other way, or both ways, or neither? Why does unitarity coexist with thermodynamic irreversibility in precisely the combination that produces the one-directional time you experience? Why does the timeless wave function assign high amplitude to configurations that look like they have histories pointing in one direction? These are not rhetorical questions. They are open research questions in theoretical physics, and the honest answer to all of them is that nobody knows. The universe is approximately 13.8 billion years old. In that time, starting from a state of such precise and improbable order that Roger Penrose calculated the odds at 1 in 10 to the power of 10 to the power of 123, it has evolved into a structure of sufficient complexity that parts of it are sitting here asking why it is the way it is. You are a configuration of matter that emerged from that improbable beginning, asking why configurations like you cannot visit prior configurations. You are a piece of the universe's history, asking about the architecture of history itself. And the answer physics gives you, that the past exists, completely and permanently, preserved in mathematics and geometry and quantum information and thermodynamic record, sealed off from you by the accumulated weight of structural features whose ultimate origin remains unexplained, is perhaps the strangest and most quietly moving thing that science has ever said. The past is real. The past is here in the sense that matters to physics, encoded in the structure of the universe, permanent and indestructible by any known process. The door is closed. The room is still there. And the question of why the door only opens one way, why, given that every fundamental law permits both directions, reality insists on only one, that question remains open. That room remains locked. And the fact that it does, the fact that the most familiar thing in human experience turns out to be one of the deepest unsolved problems in physics, is, if you sit with it long enough, the most interesting thing about the universe there is.